So I wanted to put together a quick video about a few of the different theorems that we have, because we're about to get a bunch here in 3.2. In the end, we have a few theorems that have this structure, the blank value theorem. That could be filled in with intermediate. That could be filled in with mean for the mean value theorem, and it could be filled in with the extreme for the extreme value theorem. In our textbook, the intermediate value theorem is discussed in 1.8, the mean value theorem is discussed in 3.2, and the extreme value theorem is discussed in 3.1. So I thought I'd run through. These have some similarities to them. They also have some differences, of course. But in the end, they're all saying that such and such a function must have such and such a value. It's just how that value, what that value is about, what function has that value. That's what varies between them. So first up, there's the intermediate value theorem that I have here. This is, like I said, section 1.8. The question that it's trying to answer is, must the function hit some height, the original function hit a certain height? So the idea here is we are given a function on a certain interval, and some number m, which we can think of as our target height. And so the question is, under what situations, if I'm going from A to B, and I've got some function, under what situations, if I have some target value m that I want to hit, how can I avoid it, or actually, how can I be certain it will hit that as it continues on? This happens to jump over it, whereas if I had A, B, and it was sort of a smoother curve, I'd be guaranteed to hit that value in between that high and that low. But what if I had chosen something A to B, the curve did something like this, and the M I chose was down here? Well, then I can't be sure that it hits. And so what the intermediate value theorem says is, if the function is continuous, which means this can't happen, and m is between f of a and f of b, so that's the height at a and the height at b. Well, this m isn't between those two, so that one's out. If we are sure we have these two things, continuity and m being between the beginning value and the end value for the function, it doesn't matter which one's the bigger, it could go like that as well. Then we are guaranteed that there is some input c in the interval between a and b, so that f of c equals m, that target value. So in this case, well, I'll just do this with this picture here. In this case, there's our a, there's our b. Here's blue is our curve. F of a is the height at a, f of b is the height at b. For any m that we could have chosen between these two, we are guaranteed that there's some value c that will hit, so that f of c is that target value. If m had been chosen too high, we might not be guaranteed, or too low, we might not be guaranteed. But between f of a and f of b, we are guaranteed there is a c that hits it. It doesn't tell you how to find that c. If a problem asks you to find that c, you're still on your own. You still have to solve this equation using all your algebraic techniques. All the intermediate value theorem says is that there is something to go looking for. It doesn't tell you how to find it. I also want to point out, it says that there's at least one input here. For this function, if m had been, say, down here along this line, there'd actually be two c values that produce that height, instead of, in this case, just one for that m value. I wanted to point out here, here's a case of something where the function is discontinuous, and so this function can hop over that m with a jump. Same thing could happen with an asymptote or anything like that. So that's the intermediate value theorem. Next up, I want to take a look at the extreme value theorem, which shows up in 3.1. It's about extreme values, minima and maxima. So must that function hit absolute extreme values, or when can we be sure that it does? Because maybe the function hits it, and maybe it doesn't. So we're going to be given a function f in a closed interval a, b. So from a to b, and say our function goes like that. The question is, within that interval, are we guaranteed that the function hits extreme values? Extreme maximum, or an absolute minimum, and an absolute maximum. In this case, here is our minimum, and our maximum is, well, one of these two is higher than the other, or maybe it's a tie. It looks like it's a tie in this case. There's our minimum, and there's our maximum, little m and big M. In this case, it hits them both. So there's some input that would create that minimum value, and there's some input that will make this maximum value. In this case, there seems to be two of them because I accidentally drew a tie. But what if I had something like this, and I have the function goes from a to b, and there's an asymptote in the middle, and the function does, and let's say that. Well, there's no absolute maximum in this case. There is no absolute maximum. No matter what number you say is the biggest, there's always something bigger than it. Oh, a billion is bigger. Well, you could actually hit a billion. Oh, a billion's the biggest. No, you could hit a trillion. And likewise on the other end of things. This has no maxes and no mins at all. That's easier to believe. There's one last weird case, and that is, what if we have an open interval? What if it wasn't closed? What if it was open from A to B? And our function does something like, well, it's an open interval. It doesn't actually include A, doesn't actually include B. And that's just for the sake of concreteness. Let's give these numbers 7 there. And you might say, well, from A to B, it looks like 3 is the minimum and 7 is the maximum. That's not quite true because the function never actually hits 7. 7 is what is sometimes called, once you reach higher math courses, is called an upper bound. Well, also 8, 9, 10, 7.1 are all upper bounds. They're all numbers that the function never gets above. 7 is the least upper bound. And so that's like a maximum, but not quite. Maximum is something that actually hits. The function never actually hits a height of 7, and likewise it never actually hits a height of 3. And so this has, just like this has no max and no min, this has no max and no min either. And so the question is, what makes this situation so much different than these two? That's what the extreme value theorem is trying to say. All we really need is continuity. F is continuous on a closed interval. If it's an open interval, then we run into this situation. That's why that won't happen. Since it has to be continuous, this ain't continuous. So that's going to be outlawed too. This is what it's going to end up happening. And if that's true, then, this is a little wordy, I know, there is a number c between a and b, and a number d in a and b, so that c, the input c, produces a maximum, so either a or b could end up being our c's. And f of d is an absolute minimum, so if that's our d, that's the thing that that will be the value that makes the absolute minimum. And that c and d in particular are between a and b, possibly including a, b. And when I say absolute minimum, absolute maximum, I mean only within this window. Yeah, this function gets higher, but outside the window of a, b that we're interested in. All right, so here's another picture of that, and a picture where it fails. Here we have the function being continuous between a and b. There's some place where it hits an absolute maximum, some place where it hits an absolute minimum. In this case, it's an endpoint. Whereas over here, yeah, this has an absolute maximum, but it's not going to have an absolute minimum because that's an open circle there at A. And so remember, these are all guarantee theorems. Again, this is an existence theorem that doesn't tell you how to find C and D. You got to use your old techniques to actually do that. That's what the closed interval method in 3.1 can do. But it also does not outlaw if these things aren't satisfied. That doesn't mean that this won't happen. It just means we're not guaranteed it to happen. Same thing with intermediate value theorem. You still might be able to hit those intermediate values. You just aren't guaranteed anymore. And math is about statements that are guaranteed to be true. All right. Last, I want to talk about the mean value theorem. All right. This is mean value as in the mean rate of change, not the value that's kind of indifferent toward you. This is 3.2, page 209 in the 7th edition of Stewart. Rolle's theorem was also introduced there, so they're very similar. Rolle's theorem is introduced first. It's a sort of stepping stone toward the mean value theorem. And here, what makes this different than the other ones is that must the function's derivative hit a certain value. And we don't get to pick that certain value. It's based on everything else going on in the problem. But it's about the function's derivative hitting a certain value, unlike the other two that were all about the original function having a certain height. It's about the function having a certain slope, or the function's derivative having a certain height. So we are given a function f, and we are given an interval from a to b. All right. And so what we're interested in, that certain value that they're talking about, that is going to be the average rate of change. Average rate of change of f from A to B. This is a topic that was discussed back in 1.4. That's going to be f of b minus f of a. That's the change in heights from A to B, divided by the change in x values. And so if I've got a function that goes from A to B, and does something like that, there's a f of a, there's my f of b height. Here is my secant line through there. That f of b minus f of a over b minus a is the slope of that line. And the question is, does the original function ever have that height? Or not that height. Does it have the original function ever have a tangent line with that same slope? So in this case, it looks like, yeah, it does. Right around there. So there's some number between a and b that will also produce that same height, or that same slope. And so, are we guaranteed this? Here it happened, but what makes this special? It's going to be a lot like before. Continuity is going to play a role, because if you've got a function that goes from A to B that's not continuous, for example, jump and there. If this is just a linear function, even if it's filled in there, our average rate of change is going to be a slope something like that. And that slope never actually happens, because all these slopes are like slope 1/2 or something like that, and that's slope 1/8, let's say. And so this never actually happens. So we actually don't have a slope the way we'd like it for this. And so what we need, our defining characteristics, are that f has to be continuous from a to b on the closed interval from a to b, no asymptotes on the ends. It has to be continuous from A all the way to B, and including A and B. And that's the exact same condition as intermediate value theorem and the extreme value theorem. What the mean value theorem also insists on is something about the derivative, which makes sense because it's a theorem about the function's derivative. F has to be differentiable from A to B. Maybe not at A and B itself, but everywhere in between. And Rolle's theorem has this extra condition. Rolle's theorem also insists that f of A and f of B are equal to each other. That means your heights are the same. So, for example, for Rolle's theorem, we'd be looking at something like there's A, there's B. We'd be at the same height, and now the function does something in between. But if we have all that, then there's an input C and AB so that the derivative at C has this value, the derivative has that value. So that is like I said, the average rate of change from A to B. This is the C that the function guarantees, in that the theorem guarantees there. And so in Rolle's theorem, what that turns out to be is that f prime of C has to be equal to 0, a horizontal tangent line, which we can see in this example here. There's a couple places where it turns around and we've got horizontal tangent lines. So here's another example of it. This slope is the slope of the secant line. This slope is the slope of the tangent line. Mean value theorem guarantees that we're going to be able to find, we're not on a fool's errand here, we can actually find a spot, an input, that will produce a tangent line parallel to the secant line. That doesn't seem like a big deal, quite honestly, but it really is under the hood of a positive derivative corresponds to increasing in the formal sense, and negative derivative is decreasing in a formal sense. It also corresponds to things like, well, if you know the derivative is 0, then the original function had to have been a constant function. That's something that shows up in chapter 4, and we use the constant of integration. we'll get to all of that. But it's under the hood of a lot of the little quirks and that we end up doing in this class. I don't know if I mentioned this out right or not. And for Rolle's theorem, it says it's equal to 0, but it's really the same thing that mean value tells you. Because if you know that f of a and f of b are equal to each other, then this numerator is going to end up being 0. And so, yeah, of course, it's 0. So there's nothing that Rolle's theorem says that the mean value theorem doesn't also say. So those are the blank value theorems that we talked about that are showing up in, well, in all of Calculus 1, really. We're not worrying about the proofs too much. The book doesn't even bother with the extreme value theorems proof. The mean value theorems proof really depends on Rolle's theorem, which is why Rolle's theorem is in there in the first place. Rolle's theorem, as the proof of that, depends on intermediate value theorem. So in some sense, that's why intermediate value theorem is in the book, so that we can get this, and we need this to get other things. It's all a big chain of implications. All right, thank you for watching the video. See you next time.